Right. That was just in time. So far, so good? I want to have a little bit of discussion now about the three testing principles that we have talked about. Okay, so this is extremely important. This is about principles of testing, really. So let us consider for the moment a situation where we are testing a few moment conditions. I think that is the easiest to do. So my null hypothesis is that A and B moment conditions are both valid, and my alternative is A, only A. So how do we construct a test here? Well, we have looked at three tests, and the three tests are different in the following way. First of all, let us look at the Hansen-Surgan test. So what do we do in the Hansen-Surgan test? We evaluate the moment condition under the estimator, assuming all the moment conditions are correct. Right? I deliberately put this slide up just to emphasize to you again that you have the asymptotic distribution here. It's a chi-square. Remember, you had a question before lunch? So this asymptotic distribution is a chi-square with L minus k degrees of freedom. Okay. So where is this being evaluated? What is being evaluated? What is being evaluated is Jn, and where? Let us say Jn under A and B. So it is Jn under H naught. This is not a good notation, but let me just use this notation just to highlight this point, right? So Jn under H naught. Okay? That is your J test. Together so far? Right. Let us now basically move forward to this discussion of the other two tests. Where we had the table here. The distance test is the same as the work test. Right? Asymptotically, they are the same. Where do they evaluate? And what do they evaluate? They are evaluating beta. Right? Beta where? Well, beta at the alternative hypothesis. Of course, you can look upon this as a difference as well, but asymptotically these two are equivalent. So we really look upon this as a word test. Okay? Now what is Hausman doing? What Hausman does is, Hausman also looks at beta, but it looks at a contrast of beta. Beta hat A minus beta hat AB. Okay, so now, in order to compute these statistics, what do we need? For J, we need only estimation under all the moment conditions, A and B. Just a single estimate, right? Okay? And what are we looking at? We are looking at how close the objective function is to 0. Okay, how close can you come to 0? When you do this, you again need only a single estimate. However, this time the estimate is under the alternative. So this is a word test. The estimate is under the alternative. So in terms of computation, the one which is the most expensive is this one, because you are computing your estimators under both the null and the alternative hypothesis. However, because this is like a likelihood ratio, right? So therefore, in principle, it is also the most powerful. So you are evaluating both what happens under the null hypothesis and what happens under the alternative hypothesis. Of course, it is more costly, but in principle, this is the most powerful. Then one has to ask the question, in comparison with this, of course, I told you that this is not a particularly, kind of nice test to implement, because there are problems of implementation of this test. How does it compare with the other tests? Well, this test evaluates only the null hypothesis, or only the situation under the null hypothesis. Okay, so where does it gain power? It gains power when you are close to the null hypothesis. When there is a minor, let us say, deviation from the moment conditions. In other words, you have these, which one was K, which one was L? You have these L moment conditions out there. Some K of those are satisfied, so already you are pretty close. Around that region, you gain power here. Right? On the other hand, this one, this is evaluating only under the alternative hypothesis. So where are you gaining power? You are gaining power around your A. Okay? So in some ways, when one decides which one to use and when one tries to compare across the three tests, you have to keep in mind where is which test gaining power. So sometimes what is going to happen in practice, these two tests might provide you different results. Okay? So a clear distinction between the three comes up when we also put into picture our Hausmann test. So that is why the Hausmann test is particularly important, right? So in some ways it is the most powerful test. It is in principle, however, it is hard to implement in practice. And once again, why is it hard to implement in practice? Because it is hard to estimate the variance of the contrast. Okay? So there is a first order Taylor approximation to it, which often fails. Okay, it doesn't provide a very good approximation. So that is the reason why. Right? So far so good? Okay, so let us now see how we use the GMM distance test, this guy here, to test for moment conditions. Okay, how do you do that? Well, essentially what you are doing this is, what you are using this to do is to test exogeneity of a specific set of instruments, Zi. Okay? A rank condition I'm not discussing at the moment. It will come back. We'll come back to that when we talk about identification. Once again, it is important that both the two GMM estimators are efficient GMM estimators. Okay. Remember that the way we have implemented this as a difference, as a distance GMM, we are actually computing two estimators. But conceptually, I'm saying that this is like a word test because asymptotically it is equivalent to a word test. All right. In practice, we actually estimate both models. Okay. Right. So Hansen-Sargan J-test can in principle also be thought of as a distance test. How? So that is what I'm going to argue here. The distance test, well, Hayashi actually calls it a C test. We are using the notation D here. So suppose we were confident in some orthogonality conditions, as we are typically in practice, but we have suspicions about others. Once again, like previously, we label them as A and B, like here. Okay. So we are fairly confident about these moment conditions, and we are not so sure about these ones. Okay. So can we test this hypothesis? Right? See, this test is only going to work if we have sufficiently many moment conditions about which we are sure, right? So A moment conditions has to be at least identified, right? Otherwise you can't do this. Together, guys, you should have as many moment conditions in your A conditions here as there are endogenous variables. Otherwise, you can't do it. Of course, the rank condition also needs to be satisfied. So that is only the order condition, okay? All right. And then it is all simple. So basically, we split up our instruments, okay, as A and B, corresponding moments like this. All right. So in this, we can also have the exogenous regressors as instruments as well. And typically we have those included as instruments. We have excluded instruments, so on and so forth. So we have already discussed this in the context of the Hansen-Sargan. So we believe that these are purely exogenous, right? So we do not want to test those. And there are sufficiently many there so that at least we, under this, we can estimate. Okay, so it is identified. Okay. There can be exogenous regressors in this one as well. You can also have excluded instruments there, right? So typically you will have excluded instruments. Okay. Now, these are our full set of L orthogonality conditions. These are LA moment conditions which we believe to be true. All right. And these are the additional moment conditions which is L minus LA. Okay. So that is what we want to test. How do we do this? Efficient GMM. All right. So we will be computing the asymptotic variance of this guy, right? And that matrix as well, we are going to partition in exactly the same way, right? You can order the moment conditions so that you can have that in a partition form. You see what is happening here? So this is L by L because there are L moment conditions in all right? And this one is LA by LA, and the other ones are equivalent conformable. So these moment conditions we are sure about. We are not going to test these. We are going to test these moment conditions, right? Okay. Now let us define two different GMM estimators, one that uses the full set of orthogonality conditions and one that uses only the orthogonality conditions A. Nice and simple as before. So the restricted efficient GMM estimator, which uses all moment conditions, is this guy here, right? It uses all the orthogonality conditions, A plus B. This is restricted because this works under the restriction that B is also valid, right? Okay. This is efficient GMM, okay, and it uses an inverse of S hat for the asymptotic covariance matrix of the full set of moment conditions. We want to contrast that against the other one which uses only the A moment conditions. Okay? So these correspond to the moment conditions that we do not want to test. Right? So we are sure about these moment conditions. This is also efficient GMM, but only under the A conditions, right? So you are not using the B conditions at all. So in particular, an estimate of this guy can be obtained by the covariance matrix of only the moment corresponding to only the moment conditions that you are sure about. So that's subset of G bar A. Okay. So there are two estimates here, and we define a distance test statistic, which is what? So a distance test is based on Jn, okay? So the minimized objective function under A and B minus the minimized objective function under A. All right, under A and B, we will be closer to 0. Right? Okay. So the GMM distance test D has a chi-square distribution with how many degrees of freedom? It will be LB degrees of freedom. That is clear, right? So there are LB restrictions here that we are testing. Okay? So this is this distance thing. Okay? So if this D is large, then we reject the null hypothesis. What is the null hypothesis? Well, the null hypothesis is that both A and B conditions are, moment conditions are valid. Okay? But we reject the null in favor of what? In favor of the alternative which is A only. So the null hypothesis really is about the B moment conditions here, right? Okay, because the A moment conditions, we are taking that as oracle, as gospel, right? So we do not suspect those, okay? Okay, so if you have a large D, what does it suggest? It suggests that some of the instruments in ZIB are not exogenous, right? So they are endogenous. Together, that is what this moment conditions are about, right? So what are we testing? We are testing whether these instruments are truly exogenous. All right? So essentially what that means is that not all of them should be used. We do not know which ones are valid. Okay? Yeah.
When you said the restricted GMM estimated, you mentioned that it will be closer to 0 if B moment conditions are true. Is that the case?
Yes.
Relative to
the other one, yes. Because you are placing more restrictions, right? So you can come closer to 0.
Wouldn't that get some D to become negative in that sense?
Yes, D. Okay, so yes, that makes our D to become negative. But we are not really, what are we testing here? So it is not really, just a minute. Let me check that. No. Which way do I have this? You have more moment conditions, so you are no, I've got it the other way around. Yes, you're absolutely right. The reason is that if you had exact identification, it would always be 0, right? You are moving away from 0, the more moment conditions you are including, right? Sorry, I got that absolutely wrong earlier, right? But these two will be very close to each other if those moment conditions are correct, the additional moment conditions. Yeah. Thank you. Right. So to guarantee that this is greater than 0 in finite samples, what we need to do is we need to use the same estimate S hat for computing both. That implies that we are going to use the full set of moment conditions to compute our S hat. Okay? So suppose we are doing a two-step fully efficient GMM, something that you have seen in your labs, but we are going to go into a further discussion of that in a few minutes, right? The first step, you estimate the equation using an inefficient GMM and all orthogonality conditions, right? This is inefficient, but the residuals in some ways still capture the essential properties of the errors, so you can construct your S hat from those consistently. Okay, you have done that. Once you have done that, you use the inverse of this as the weighting matrix for efficient GMM. Okay, so that is a two-step GMM. And when you are doing it only under the A assumption, that is under the alternative hypothesis, then you only use S hat AA, inverse of S hat AA, right? But they are both based on the full set of moment conditions. So you don't need a new set of first step residuals to construct S hat AA. In fact, it is advised that you don't do that. Asymptotically, you will be correct if you did that, but you cannot ensure guarantee that D is greater than 0 in finite samples. Okay? Okay, so now let us go back. So that was the distance test, right? For moment conditions. Let us now go back to the Hansen-Sargan J test for moment conditions and see how do these two compare. So what I'm claiming here is that the Hansen-Sargan J test can be interpreted, well, the Hansen-Sargan J test can certainly be interpreted as a joint test of orthogonality conditions, but I'm also claiming that it is also a GMM distance test. Now, why is that so? So what is my distance test? Distance test statistic is Jn beta hat minus Jn beta tilde, where this beta tilde is under a restricted set of moment conditions, right? A only. What is my Hansen-Sargan J test? That is this guy. Where is this computed? This is computed under A and B. So where is this guy here? The second component. Together, guys? Are you following this? So, everybody together so far, sorry, where are we? Yeah, basically the distance test, we are together on that, right? Okay? Right. Now I'm saying that the Hansen-Surgan J-test can be interpreted as a distance test. Right? What is a distance test? A distance test is this guy, right? Okay? If you look at the Hansen-Surgan, that only has this. Beta hat is under the null hypothesis. Okay? What is this guy here? Well, this guy is, so what are you testing in Hansen-Surgan? You are testing the full set of moment conditions, right? So what is the alternative there? The alternative is the minimum set of moment conditions which makes your model identifiable, right? If you have the minimum set of moment conditions, what is the value of this? It's precisely 0, right? Because you can set it all the way down to 0, right? That is your IV. Okay? So that is 0. So therefore, this is also a distance test, but that is somewhat hidden in the formulation here, right? So Jn beta tilde here is 0. So you don't need to compute it. So what is the alternative here? The alternative is the minimum set of moment conditions which are valid and make the system identified. But we cannot be more specific than that. So we are not being more specific than that. It is also a distance test, but against an alternative which is just identified. Okay? So the restricted estimator beta hat is the estimator when we assume all moment conditions. Okay? So in this case, your distance test becomes simply Jn beta hat. Yep.
Can you repeat what the alternative hypothesis was again?
The alternative hypothesis for the Hansen-Surgan J-test is any set of exactly identified moment conditions. I don't care which one. Which ones? Take the first K. Or any other set. Means whichever set is exactly identified, it doesn't matter because this guy is exactly 0 for that, right? I don't really need to compute this. Yes?
So we can interpret it as testing whether we have an exactly identified model or have we got extra identified.
That is right. Beyond an exactly identified model, whether we have over-identifying restrictions. That is why it is called an over-identifying restrictions test. All right? Yep.
But again, it contains no information of what the exact identification
Yeah, that is right. If you want to do that, what do you need to do? Set out separate tests of, sets of moment conditions and test one against the other. That lands you up into problems of p-hacking, right? But, in terms of principle, you can do it, right? And in many practical situations, people do it all the time. Means we are going to look at, other conditions in a little bit, maybe next week or the week after, where there are lots of moment conditions and you do not know which ones work. In these kinds of situations, many people run a horse race, right, on the machine, trying to find out which ones work, right? That is fine, provided you also take into account the fact that you are running hundreds of tests there, right? So just by random chance, some of these will not be rejected, right? Okay, so you have to adjust your significance level to that. That is called multiple testing. We are going to come back to that later, right? But again, means I pointed this out in the previous lecture. One of the important names in this literature of running this horse race, etc., which is very popular, is Rudman, right? So it shows us how to do this appropriately, but it is not easy to do it. But yeah. Okay. So we can easily test orthogonality conditions for particular excluded instruments, right? Using a distance test. You estimate the model using all excluded instruments, and you obtain this Jn beta hat, and then you obtain this Jn beta tilde. If the difference between these two is large, you conclude that the instruments you dropped were actually endogenous, right? So if they're exogenous, they should give you something very similar. However, I've added or something else is wrong, because there are other assumptions in the model, right? So which particular homogeneity is an important assumption that we have made all through. Okay, so there might be problems of that. Also, there are problems of where the instruments are valid, right? So the instruments may be valid on one set of the data or one segment of the population, and kind of another instrument may be valid on another segment, right? So those kinds of problems may be there. Okay, this is just about the details. Yeah, so this is just repetition. This is about the details. This one is important here. So suppose that independence and conditional homoscedasticity both hold, then both IV and OLS are efficient GMM estimators. Okay, then the distance test is an alternative way to compute a endogeneity test, standard endogeneity test, and an earlier endogeneity test which goes by the name of Durbin, Wu, and Hausmann, right? So see, we started from the Hausmann, then modified it with Wu and Hausmann, and then Durbin, Wu, and Hausmann, right? So that is the form of the test which is typically used. However, this one here, the distance test, has an advantage. What is that advantage? The choice about what variance estimator to use for the moment conditions is left to us. All right? Depending on the situation, we can use a heteroscedasticity consistent estimator, we can use a cluster robust estimator, or a hack estimator, so on and so forth. So that choice is left to us. By using this choice cleverly, we can actually conduct this test in a much more robust way, which was not available with Durbin, Wu, and Hausmann, right? Okay, so that is the advantage of conducting this test, endogeneity test, in this form, in the GMM distance form. Okay? Otherwise, these two are equivalent. They are asymptotically equivalent. Right, a few special cases now. First of all, let us consider a situation where there are no endogenous regressors. So K2 is 0. All regressors are exogenous. We still have excluded instruments. Okay? Now, we can estimate using OLS. However, we have some excluded instruments anyway. Okay? So this is similar to the AJR example that we have looked at. So institutions are perhaps exogenous in themselves, but you still have settler mortality, which is also exogenous. Okay? Or a wage equation where education is actually exogenous, but schooling laws are also exogenous. Right. So then what do we have? Our model looks like this, and our moment conditions look like this. Okay? If we have conditional homoscedasticity and independence, then OLS is most efficient. Actually, we should not be doing anything else. Okay? even if the equation is over-identified and we have excluded instruments. Okay? So excluded instruments, these are not going to add to the efficiency of the estimator. So in this case, these additional moment conditions, they are called redundant, right? So they are not contributing anything. So we can compute a Hansen-Sargan J statistic here, right? Under conditional homoscedasticity and independence, this is simply the Sargan statistic. What does it do? If we relax the conditional homoscedasticity or independence assumption, now, however, OLS is not efficient. Okay, we can obtain an efficient GMM estimator using the inverse of the robust S hat. And here again, we can do a Hausmann-Sargan J test. Okay, so the two-step feasible efficient GMM here in this condition was developed by Krag in the conditional heteroscedasticity case, and here the appropriate WN is this guy here, right? So it is heteroscedasticity consistent. Okay, it is sometimes called heteroscedastic OLS. All right, but instead of this, one can use hack as well, right? And that is easy to do, or cluster robust, etc., or any other efficient GMM estimator, right? Why is this useful? So OLS here is in principle adequate, right? So the other instruments, there might be instruments, but these are basically redundant. In other words, what is the interpretation of the Hansen-Sargan statistic here? Now we have already seen this interpretation of the Hansen-Sargan test, and this is what we have been focusing on, but the Hansen-Sargan test is a bit more than that, right? So let us see this. Consider an alternate model where the instruments Zi appear as regressors. Okay, so maybe there are additional regressors here. Again, going back to the AJR case, institutions are exogenous, but settler mortality also in principle affects economic development now. Okay? Well, suppose that were the case. Now, here what I've done is that I've added some subscripts to the betas to emphasize that there are these X and Z, right? So this was what original, so think of this as institutions and think of this as settler mortality. Okay? So you might want to perform a GMM distance test that this guy is equal to 0. Okay, that settler mortality does not matter. What is the GMM distance test? That is precisely this guy. However, the unrestricted model is exactly identified, so therefore this guy is 0. So what is this? This is really your Hansen-Sargan J test. Okay? So the Hansen-Sargan J test, J statistic here, is an alternate test for the hypothesis that beta 2 is equal to 0. Okay? So this is same as the Hansen-Sargan statistic for over-identified model with no endogenous regressors. So one can conduct the Hansen-Sargan J test in a situation when there are no instruments or no endogenous variables, but the interpretation is different, right? Why does this interpretation come about? It comes about partly because the Hansen-Sargan test is an omnibus test, right? So it tests all the conditions. So this was our original model, first model. This is our second model, right? The Hansen-Sargan J test is identical to the GMM distance test for beta 2 equal to 0 in model 2, right? So lesson is that we can interpret a large J in model 1 in two ways. One is that this thing is right, okay, but this guy is not equal to 0. Or you can interpret this as saying that this thing is wrong because Zi's belong to regressors, right? Which of these is correct? We cannot say. Okay, so that is a sort of Mickey Mouse example, but I'm bringing this in just to emphasize how you interpret the Hansen-Sargan J test, right? So it is tricky, so you're considering different situations. Okay, that's about it for specification testing. Okay, if we are together so far, let us give it 1-2 minutes in case there are questions. Otherwise, we'll move into the properties of the efficient GMM, which we have not done yet. So we have looked at today, we started off by properties of the GMM, right? Asymptotic properties, consistency and asymptotic normality, right? We now want to look into the efficient GMM, but before that, let me just stop a minute just to make sure that we are together on the 3 testing principles, the 3 kinds of tests, all right, and what they deliver. I'm coming to you, yes, to both of you, yes. You first, yeah.
So can you give an example of what a restricted versus an unrestricted model would look like if we were testing them? Like, let's say the last. Is the restricted with the instrumental variables? Or what does that look like?
Let me just do AJR, right? Because that is what you have done in labs. Okay? My restricted model would might look like, or the null hypothesis for the restricted model might look like, settler mortality and geography. Are both exogenous. I'm writing this in full form, right? Okay, just to get the concepts there. What is my alternative? My alternative is that geography is exogenous. Why? Because geography is really geography, right? It has been said before, before the beginning of time. The locations of the countries have not changed. They cannot change. The latitude of the countries cannot change. So it's purely exogenous. Okay? So what is my restricted model here? My restricted model is this. And this is my unrestricted model. Sorry. Okay? right? In this case, what is my Hansen-Sargan J test? My Hansen-Sargan J test just computes Jn under H naught. What is my distance test? My distance test computes both of these, right? And looks at the difference in the J value. Okay? However, here, how many endogenous variables do I have? I have only institutions, right? Let us say I. So this one here is exactly identified, right? This is exactly equal to 0. Right? So in this case, these two coincide. Coming to you. Does this answer your question? Right? You first and then you.
Okay, my question is regarding the previous slide.
Yeah.
We say that there's no endogenous regressors, but we have instruments. Why is that, and when will we need it? I mean, we don't have endogenous regressors, then why do we have these?
No, so that is precisely the point. So a large J might indicate that this is not correct, but who cares, right? Or it might indicate that your beta 2 is not 0, in which case it should be there in the model potentially, right? So the whole point of doing this was just to emphasize that the J test, the interpretation of J test is a bit tricky, all right, because it is kind of an omnibus test. So it is not a direct test of moment conditions. Okay? So one has to be a bit careful about interpreting it.
What are the Z instruments for the, what are we instrumenting? That's what I mean.
Oh, right, okay, so these Zs are my instruments. Nothing, they are just excluded variables. They are just excluded instruments. So, these moment conditions potentially, so think of this. These moment conditions are potentially valid. The question is that whether I want to use those moment conditions or not. A point is that if beta 2 is equal to 0, there is no point in doing that. Okay? But if we conduct a J test, I think I was just seeing a moment earlier, some of you guys brought one example to me that you have done in your labs. This was example 3, I think. That is about this kind of situation, right? You do not have excluded instruments, but you are still conducting a J test. Why? What does it tell us? Okay, so you don't need to, use those instruments, but and the additional information, it is not clear that it is not going to provide any efficiency as well, right? But here the point is basically to emphasize the point that basically the J test is much more, so it is an omnibus test. Yeah. Yes.
Okay, I'm still confused about the restricted and unrestricted terminology.
Have I got it wrong again?
If I understand it right, then yeah, it should be the other way around. So
Yes,
it's
it should be.
unrestricted that we impose as little restrictions on the variables as possible. So only the bottom case where we have only one variable
Yeah.
is supposed to be restricted.
Yeah.
And
You're absolutely right.
above we have a few such.
Yeah. Sorry about this. Okay. But you get the point of what I was saying, right? So, yes.
Still about the J-test actually. So it's just a test that we have some model and we can test whether that model is wrong, but there's absolutely no further information in it. So
Absolutely right.
it is like we have to have a fairly good idea of what could go wrong with our test if we want to actually use the J-test results. Because otherwise we'll just know that we were wrong somewhere and it tells us of like no useful information in that sense.
Yeah, that is precisely what I'm trying to emphasize all along. You can interpret the J-test as a test of moment conditions, but only when you are sure that everything else is correct, right? Because the J-test will fail if anything else in this model goes wrong. And there are a lot of assumptions in this model. It is not only the moment assumptions. It is true that the J-test is typically interpreted as a test of moment conditions. But that is not the only interpretation of a failure of the J-test. By the way, it gets more complex than that. Just because you have failed to reject the J-test does not tell you also that your moment conditions are correct. Why? Let us take the example of education and wages, right? So you are regressing wages on education. Maybe you have some measure of ability as well, so that is not the problem. Okay? But education itself is endogenous, right? Why? Because education, how many years you get educated partly depends on your expectations of what your future wages will be. So it is potentially endogenous. So you need something as an instrument. What is a typical instrument? Typical instrument may be mother's education, let us say. But why only mother's education? You have father's education as well. Okay, fine. So now you have over-identification, you have two instruments. You have conducted a J-test of over-identifying restrictions and you failed to reject. Okay, in this case, it is very hard to argue and it would be very wrong to argue that therefore your moment conditions are correct. Why? Because if mother's education were not an appropriate instrument, father's education probably would be wrong for the same reason, right? So these look like two different measures, two different instruments, but they are not really two different, coming from two different principles, right? If one is wrong, the other one is wrong as well, probably. So maybe both are equally wrong, and that is why you do not have, you are failing to reject the null hypothesis of the J-test, right? So J-test is actually very useful, but you need a lot of thinking to apply it well. Do you get this example? Right, it's a very common example. It happens all the time. And you know, I suppose Mark will also emphasize this in the labs because it happens quite often. You have to think through, where is the identification coming from? What kind of instrumental setting? There was a little bit of discussion in the AJR case that we had on one of the slides. So, settler mortality and geography, maybe they act in the same way, right? Maybe settler mortality depends on geography. So if one is wrong, probably the other one is wrong as well, right? Except that you think that geography is correct. Why? Because, you know, it's geography, right? It's latitude. Okay? So one needs a nuanced argument there, right? Okay, all is not science here. Okay, so, so just think through. Anything else? Okay, 5 minutes. Okay. Thank you.
It's just it feels like everything is looking into general.
All right, guys. Any further clarifications at this stage? Conceptually, are we doing okay? All right. Any other issues that arise? None, right? So about testing, everybody is fine. What we are going to do is take a step back now, get back to our feasible, efficient GMM. Right. Yes.
So if we go back to the no endogenous variable component, if you already know that there is endogeneity, for what reason would you then apply the instruments as basically controls rather than actually using them as instruments? Why would you do that?
Well, if you know that there is endogeneity, you need instruments.
Yes, but why would you then do this instead of putting them as instruments? Like if you put them basically as Z, B to T.
Sorry, I don't quite understand. So, you are saying you know that X is endogenous.
Yeah.
If you know that X is endogenous, then you need instruments.
Yeah.
Period. All right? Now, you also need excluded instruments, right? Because otherwise you are not satisfying certainly the order condition. Okay? So just by having controls is not going to be enough. Okay, so you need excluded instruments. Where you get them from is a matter of that specific application, is a matter of that specific context. But you will need instruments anyway. Suppose you have several controls there, which are all potentially controls or potentially instruments as well. Then a question arises as to whether you can use some of those as instruments. Whether you can or not is an empirical question. You can do this test sequentially to try and find out what can work as appropriate instruments. But if you have endogeneity, then you need instruments anyway. This controls is not going to help. Is that okay? Right? Yep.
And if you had an idea which one you want to use as an instrument, could you just use either the wall test or a distance test? Then you're testing against that specified alternative of using just the restricted set of instruments. Conditions.
The first port of call is the Hansen-Sargan. Because, yes, the Hansen-Sargan does not exactly tell you what is wrong with your model, but it tells you that something might be wrong. All right? Or it tells you that something is wrong, provided you reject the null hypothesis. Then you want to go back and find out what exactly is wrong, and that is where you need this specific tests which give you powered against specific directions, right? So, in a real world situation, it is a bit more complicated, right? So then you have to go into all of that. And you will be coming across this in your econometrics projects, for example, because there will be these kinds of situations. You'll have to, balance out one against the other. You'll have to argue and so on, right? Here we are discussing principles, but, you have to use, these tests are available. How you use them in a specific situation and how you argue about their use is all part of the skill set, okay? I'll say one other thing. Precisely for the reasons that we have been discussing, finding instruments is not very easy. Finding instruments typically still, you basically lean on the shoulder of giants, right? So essentially, you look into the literature to find out what instruments people have used, why those are argued as appropriate instruments. It takes a lot of skill to find instruments. Now, finding out whether a specific instrument is adequate or not is a bit easier. You can use your test to do that. But finding instruments is not, kind of, if you went into the AJR, kind of situation, for example, and you were doing it on your own, arguing that settler mortality might be an adequate instrument is a huge deal. No, it's not very easy, right, to find an instrument there, right? So that is a very challenging problem. Finding appropriate instruments is hard. Okay? Right? So, efficient GMM. Let us go back to the GMM first of all. So I've already seen this. You have already seen this. Right? So we start from there. Suppose here you substitute for W with S inverse. So in other words, you choose your W as S inverse. Then this whole thing collapses to this. Okay, that is just simple matrix algebra. Okay, a lot of terms cancel and the whole thing collapses to this. And the moment you look at this, because you have done GLS and stuff like that, you will recognize straight away that this looks very familiar to an efficient estimator, right? So that is what the variance of an efficient estimator looks like. So you think that once you have this kind of structure, simple structure, then maybe this guy is efficient. Suppose that were true. And we are going to show in a few minutes that is true. Now, suppose that were true, then that obviously offers straight away a simple way to construct a feasible efficient GMM. How? Because you can estimate this guy from the data, right? You can get a feasible estimator. Okay? So once you have obtained your first stage GMM, you compute your residuals then give you the moment conditions, the covariance matrix of the moment conditions you can compute. So you can robustify it using various things, heteroscedastically consistent, cluster robust, hack, whatever is appropriate in a particular situation. But anyway, you can find a estimator of this guy. And once you have done that, so this guy, once you have done that, you know what to substitute. So that is a feasible efficient GMM. All right? But let us now spend a few minutes to try and see why this is efficient. Okay? So here I have only a sketch, but well, it will provide the main ideas. Okay? The full proof is available in Hayashi. So this is the variance of GMM, asymptotic, and this is of efficient GMM. What does it mean to show that this choice of W equal to S inverse is efficient? Well, if you can show that this guy is larger than this, you are done, right? So if you had any arbitrary GMM with some W, right? If the variance of that would be at least as large as this, or in other words, this is the smallest variance that you can have, then that is your sufficient. That is sufficient. So basically what we try to show is this variance of GMM minus variance of efficient GMM. These are all asymptotic, right? So this is asymptotic efficiency we're talking about here, right? Okay. Right. If A and B are symmetric and positive definite, then A minus B is positive semi-definite if and only if B inverse minus A inverse is positive semi-definite. So that is the property that we are going to use. Right? So what do we want to show? We want to show that this guy F, which is this, what is this? This is this guy here minus this, which is the inverse of this, right? That is positive semi-definite. If we can show that, then this is also positive semi-definite. So we have this minus this is positive semi-definite. Together? So that is the line of proof. All right. So this guy F is this minus this, which is this. S is positive definite. Why? It is a variance covariance matrix, and which obeys the rank conditions, right? There are no redundant instruments there. S is positive definite, so if S is positive definite, then we can do a decomposition like this. What is this called? This is called the singular value decomposition, right? Or the Cholesky, one of those. CC prime is equal to S inverse, and C inverse, C prime inverse is S. Okay? So then we find the following. This F guy here is H prime mg H, where H is simply this, and mg is an idempotent matrix, symmetric idempotent matrix. It is a projection matrix with G like this. Okay? That is simply by substitution. Okay? Okay. Now, what is this guy here? This guy is like a quadratic form. Okay? So it will be positive semi-definite if this guy here is symmetric and positive semi-definite. Okay? So this guy is this, with this plugging in these values. Mg here is symmetric, right? This is Mg, that is symmetric. It is just a projection matrix. Okay? It is also idempotent. All right? What is importance of idempotence? Well, it is. It shows that it is a projection, right? So once you have projected once, if you project again in that direction, you don't get anything new, right? You have included all the information. Okay, so then this thing is like this, which is this thing here. Okay, now a little bit of matrix algebra or matrix principles. Suppose this was a scalar, right? So suppose this was a scalar, then it is clear that if we have this, then that is greater than or equal to 0, right? Because this is just a square. Okay? In more general cases, F is still a positive semi-definite matrix because this is like a sum of squares. Okay? So then, this thing is positive semi-definite, and therefore this guy is guaranteed to be positive semi-definite. What is this showing us? This is showing us that variance of any GMM, asymptotic variance of any GMM, cannot be smaller than this guy. In other words, this is the most efficient. Okay? Yeah.
Why is it the most efficient and not just more efficient?
Oh, because no other GMM can beat it. That is why it is the most efficient. Right? So this is any GMM, right, with any W. I will show this with any W. Okay? In particular, it is true with identity, it is true with anything. Whatever W you place there, it is not more efficient than this, so this must be the most efficient. Got it? Right? Right. So that is our efficient GMM estimator. So now let us look at a few features of this efficient GMM. IV as an efficient GMM estimator. Suppose we had conditional homoscedasticity and independence, then we can use IV. What is IV? So in this case, your S is expected value of GI prime, and you are just picking up these epsilon I squares here. Okay, so this thing is just this quantity here, right? Okay, and this we can estimate easily using your classical estimator. Okay, classical IV estimator. Okay. So this is my classical estimator of the S hat. What do I get my sigma hat square from? We could estimate it using the residuals, like we have said earlier. But actually it turns out that we do not need to do it. Why? Because the GMM estimator is invariant to scalar multiples of the weights matrix, so it just drops out. Okay, so you don't really need to estimate this guy. Okay, it cancels out. So if you substitute this here, you find that your beta hat GMM is simply this, so there's no sigma square here, right? The sigma square, there are in two different places, and it just cancels out. Okay, one against the other. So this, what is this? This is simply IV. So therefore, IV is an efficient GMM estimator. Okay? Under the assumptions of independence and conditional homoscedasticity. Okay? Why are these conditions important? Because that is when you can use this classical S hat, right? Otherwise you can't. The IV estimator is also two-stage least squares. What do we mean by that? Actually, the IV estimator is much older than GMM. It was discovered in a different context. Should I go into the story? Should I not? Let me not go into the story now, right? But we can come back to this later on. It was actually discovered in a pretty nice setting. and it's a great example of interdisciplinarity actually. So it was discovered by two Wrights, not brothers, but father and son, right? One was a biologist, an ergonomist actually, and the other one was an economist. So there was an ergonomic problem which Philip Wright, his son, actually solved, and that was in 1930s, I think, or 1920s actually. So they discovered it. So it came much earlier. Okay. Now in the literature we refer to this as two-stage least squares. Why? Well, we have seen the example earlier, right? The supply and demand example, right? So you basically think of this as moving the supply curves down to the demand function, same demand function, right? So that we have seen earlier. So we can do it in two stages. Okay. However, that is not how we do it in practice. We do it all together. How do we do it? Just by this, right? So don't do it in two stages. Why do we not do it in two stages? Because it doesn't provide correct standard errors, right? So the mistakes in the first stage or uncertainty in the first stage has to be incorporated into your calculation, right? So that is why we don't do it in two stages. We do it all together, right? And with using this projection matrix here. Seems I might have destroyed this. Let's come back again. Right. So really, an IV estimator is like this, which is really like a GLS, right? Yeah. So this is what an IV estimator is with a particular projection matrix. It is a projection matrix. How do we know it is a projection matrix? The same drill as earlier, right? It is symmetric and idempotent. What is a projection matrix? A projection matrix is a matrix which is symmetric and idempotent. Because it is idempotent, so then if you apply it repeatedly, you don't get back anything new. You have projected it once, and you have projected it in the right direction, right? So therefore, with a transformed set of regressors, this is actually OLS, right? Now what is that? That is a GLS, okay, with a particular transformation of your XLs. So this is the formula for OLS, but using fitted values of the XLs as regressors. That is why we can do it in two stages. So this is my IV then, which I can obtain in two stages. In the first stage, I regress all the XLs on the instruments and obtain fitted values. These are first stage regressions. Then using OLS, I regress the dependent variable y on the fitted values of x tilde. And this is an artificial regression, and the slope of this is beta hat IV. The standard errors will be wrong when you do it this way. Right. In the past, this has been used as a calculation machine, right? Because regressions, standard software was available for that. But now we just used an IV formula, right? Emphasized here that it will give you the right slopes, but the wrong residuals, and therefore the wrong asymptotic variance, right? So the asymptotic variance needs to be corrected. So therefore, I've also said that the name two-stage least squares is misleading because you don't really do it in two stages, right? This is quite different from three-stage least squares and stuff like that, right? Where you really needed to do it in several stages. Here you don't need to do it in two stages. This is also very different from two-stage GMM, which you need to do it in two stages. But two-stage least squares is not quite done in two stages. You do it all together. Right? These first-stage regressions are useful for other purposes. I'll be coming back to that. Okay, so when we talk about identification, that will be next time. We can also look upon IV as an inefficient GMM estimator. Why? First of all, intuition. Suppose you had multiple instruments, so you had over-identification. Or what are you doing? In IV, you are projecting your excess, endogenous excess, in the direction of the Zs, right? Your instruments. Okay? When you are doing that, you are not keeping in mind that you can potentially weight your different moment conditions, right? So you are treating them all as equally important. That is like doing first stage GMM with an identity weights matrix. So that is not an efficient GMM. So it is an inefficient GMM estimator. IV is an inefficient GMM estimator. So, okay. So you get this guy, this robust to heteroscedastic. So you can use an IV estimator, but with an asymptotic variance which is robust to various things, etc. You can just use a sandwich estimator formula for the variance of an inefficient GMM estimator. That is simple to do, right? So these guys are estimated by this guy is estimated by this guy, right? You don't need sigma hat square, which we have seen earlier, and robust S hat for your choice. And that is quite commonly done. However, the same principle, right? So you are not making efficient choice of moment conditions here. Okay. So this is inefficient IV rather than feasible efficient GMM, right? And this guy makes more demands of the data, and finite sample performance may actually be worse than an inefficient IV. And therefore, it is still sometimes an estimator that you might prefer to use. Okay, so it's an empirical question. What do you usually use? What do you mean by GMM? Or the standard GMM that you use? That is a two-step feasible efficient GMM. So what are you doing here? You need an estimate of S. So you need first of all any consistent beta hat. What do you get in a consistent beta hat? Well, you can do a first stage GMM with whatever. Let us say identity matrix as your W, because that is the easiest to compute. That is like your IV. Okay? So in principle, any weighting matrix will work. We would like to use something that is not very inefficient. So you choose something. And once you have used this inefficient GMM, you obtain the residuals and then use the residuals to compute this guy, and then use this hat to obtain S hat to obtain your feasible efficient GMM. So that is two stages, right? Or two steps, right? First an inefficient GMM, then you collect residuals, you estimate your S, then you do feasible efficient GMM, right? Why don't you continue? In principle, you could continue, right? So you do your two-step, you obtain your residuals again, you estimate your S hat, and do it again, and then onwards and onwards and onwards. Okay? That is also an estimator. That is called an iterated GMM. Why don't we do it? Because We know that asymptotically this is efficient anyway. So why do we bother? Right? There's no guarantee that if we do it 3 times or 4 times, first of all, that we are going to get convergence. Secondly, that we are going to get anything which is, well, we're certainly not going to get anything which is asymptotically better than this. So that is why we stop here, typically. But it is important to emphasize that we do not stop at the first step, right? So at least we want an efficient GMM, not an inefficient GMM, right? So we do it in 2 steps. So these are the steps, basically. Very simple. Step 1, you obtain beta, estimate beta and obtain a consistent but not necessarily efficient beta hat GMM. Okay? Then you use the residuals to obtain a consistent estimate of your S. Whatever. It depends on the context, right? You use your S hat inverse to obtain this guy and this guy, okay? And that turns out to be this formula. What do you choose as your first step? Well, the natural one, right? You can just choose IV. What is IV? IV is simply GMM with W equal to I, the identity matrix. That's what it is. So I can choose that. IV is not too bad an estimator, right? So, you know, kind of, we are not doing too badly if we choose IV as the first step. Okay? So in that case, your W is just your identity matrix. Iterated efficient GMM, well, I've just described what it is, right? So continual iteration. It is rarely used because it does not yield any asymptotic efficiency improvements. It's the same principle as GLS. Maybe it was discussed earlier in your GLS lectures, I do not know. GLS in principle you can continue till convergence, right? Why stop at, well, 3-stage least squares, why stop at 3 stage? You can go to 4, 5, 6, 7, you know, you can iterate this. Why don't you do it? Because it doesn't provide any asymptotic efficiency. Okay, so the same principle. But if you are doing this iteratively, it might yield small sample improvements. Particularly when your estimator S hat is very inefficient. However, that is very context specific. So it is in general not used. We are going to see later on that there are some situations when iterating in this particular way actually leads to better finite sample efficiency. That does not happen, that happens when? Typically when your errors are normally distributed. We are not assuming normally distributed errors here. Okay, so we don't get that. In fact, one of the reasons why we stick to GMM is because we do not want to assume normality of the errors. Okay, so we are working with moment conditions. All right, what else? There's something called continuously updated GMM. Okay, where does that come from? This S hat uses residuals from an estimated beta naught hat. Okay, so S hat really is a function of beta naught hat, right? What are you doing? What is the GMM objective function? The GMM objective function is this thing here, right? Except that we had an S hat here, now we have plugged in a beta naught hat as well. So to emphasize that this is a function of beta naught hat. Okay? Now having written it in this way, one can just minimize this, right? Okay? If you do this, then the estimator that you obtain is called a continuously updated GMM. How do you obtain it? Well, obviously there are no closed form solutions here, right? So you have to do numerical minimization, typically in large dimensions, right? So beta can be large, right? So that's not very easy. It has some nice properties because you see you are doing it all in one stage all together, right? So there are potentially finite sample efficiency considerations there, but it requires numerical methods, and there's no closed form solution. So typically this is not used, it is used rarely, all right, but it is available. With one exception, which is limited information maximum likelihood. In some cases, particularly when your errors are normally distributed, you can interpret your GMM as a maximum likelihood estimator, or particularly this continuously updated GMM as a maximum likelihood estimator. Okay? So this was also something which predates IV two-stage least squares. This was introduced by Anderson and Rubin in the 40s, late 40s. Late 40s was an interesting time for developments in this literature, right? So a lot of interesting things happened at that time, just after the Second World War. So what is this limited information? It means that it is a maximum likelihood estimator, but for a single equation, right? So you have a system of equations, but you are obtaining maximum likelihood for a single equation. I'm not going to go into further details of this right now, but we'll come back to this when we discuss maximum likelihood, right? Because it is interpreted as maximum likelihood, it has some advantages. Okay, so the full information maximum likelihood is the maximum likelihood estimator for a system of equations. This has a closed form expression, but as a solution to an eigenvalue problem. So you have to make an eigenvalue decomposition of your entire system, right? So that is costly. So then a limited information maximum likelihood is actually an efficient, continuously updated, efficient GMM estimator under conditional homoscedasticity and independence. So in some ways, this is to LIML is to CUV what IV is to two-stage feasible efficient GMM, right? So there's a connection between those two things. Right. So that's where I stop. There may be typos in here. So please, yes.
So when you say it's costly, what do you mean by that? Like when you view an estimate as costly, or you say it's specific, yeah.
By costly here I mean it's computation intensive.
Computation intensive. Okay.
If you want to do numerical maximization or minimization in more than say, let's say 5 dimensions, it's actually very hard to do. But we'll be coming back to this issue later on when we discuss maximum likelihood. So remind me at that stage, right? So I'll have a more elaborate discussion of this. Anything else? Any other questions? Okay, big days, but everybody together, right? So next time we'll move into identification, and yeah, we'll kind of. Is the pace okay with everyone? As last time it was a bit rushed, and I accept that. But this time I've tried to go slower. All right? Okay, thank you.